I'm going to use the video game niche to demonstrate the Hardy-Weinberg equilibrium principle and how it can be used to model changes in allele frequencies over time. Hardy-Weinberg equation relies on the assumption that you have a large, random mating population that is not affected by mutation, migration, or natural selection. These assumptions are met, both the allele frequencies and the genotype frequencies will remain constant from generation to generation. On our island, we have a population of cat-like creatures, and at the loci for leg type, there's two different alleles, big A, which is fishing leg, and little a, which is running leg. Our population is in Hardy-Weinberg equilibrium, and we have 12 big A, little a individuals, 6 little a, and 6 big A. Let's calculate the allele and genotype frequencies for our population. In this case, 50% of our alleles are big A, and 50% of our alleles are little a, so our gametic array is 0.5 big A plus 0.5 little a. Our genotypic frequency is 6 out of 24 big A, 6 out of 24 little a, and 12 out of 24 big A, little a. So our genotypic array is 0.25 big A plus 0.5 big A, little a plus 0.25 little a. We can use these numbers in the Hardy-Weinberg equation, which states that P plus Q equals 1, where P is the frequency of big A alleles and Q is the frequency of little a alleles. We can also say that P squared plus 2PQ plus Q squared equals 1, where Q squared is the frequency of big A, 2PQ is the frequency of big A, little a, and Q squared is the frequency of little a genotypes in the population. Now if we apply selective pressure to this population, for example, let's say that heterozygotes at this allele are more likely to reproduce. Now we're violating one of the Hardy-Weinberg assumptions because we're selecting for heterozygotes. This type of selection is called stabilizing because although heterozygotes are favored, both big A and little a are going to maintain in the population. This is what it would look like on a graph. Another way to think about this is to say that we're selecting for a non-extreme trait value. Now that we've applied the selective force, let's recalculate the allele and genotype frequencies for our population after stabilizing selection. Our initial frequency of heterozygotes was 50%, while our frequency of big A and little a was 25% each. After a generation of stabilizing selection, the frequency of heterozygotes has increased to 67%, while the frequency of big A and little a has decreased to 14% and 17% respectively. If we continue, our population will become increasingly dominated by heterozygotes. I let this scenario play out in the game, and as you can see, most of my creatures are now, in fact, heterozygous at this locus.